structures your life. You move on it, you live in it, and are surrounded by it at work and play. We take its strength for granted, but it isn't indestructible. Is it possible that when damaged, new buildings have the power to heal themselves? The answer is yes. Concrete structures, like bridges, are actually composites of concrete embedded with metal. They take a beating over time. Cracks and fissures can weaken structures, putting them and the people who use them at risk. But new materials, like shape memory alloys, can be used to create smart structures that sense fractures and, in effect, heal themselves. Concrete has a longer history than you might think. Examples go back to the ancient Mediterranean world. Before concrete, there was stone, which was heavy and expensive to mine. There was also mud, which wasn't sturdy, and wood, which wasn't durable. Concrete allowed the Romans to create monumental interior spaces like the Pantheon and amphitheaters like the Colosseum, both of which are still standing. We still use concrete to create modern gathering spots.
In our society and in our world in general, concrete has become the most used building material. It's used because it can be cheaply manufactured and has been used for all kinds of structures, stadia, housing.
But there's a big problem with concrete.
The disadvantage of concrete is it contributes 5% of the total amount of carbon dioxide emission in the atmosphere. That can cause greenhouse gas effect and potentially the climate change as well.
So today, we're looking to make concrete not only smarter, but also greener.
So Zerocrete is concrete type material. Zero means zero carbon emission. So it's actually zero C-crete. So that's why the name Zerocrete came. The process is a very low temperature process, around 100 degrees Celsius, as opposed to cement production, which is 1400 to 1500 degrees Celsius. So essentially, we don't emit any carbon dioxide type material in the atmosphere. So myself and Dr. Hinch, who are co-inventor of this process, has been looking at reducing pollution to the atmosphere and the greenhouse gas effect. And we see that in our modern day civilization, you need power, you need electricity. And there are many coal-fired power plants out there. They produces so much amount of fly ash, which is a product of the coal burning. And this fly ash actually goes to landfill, and it can be a hazard. So if somehow we can use this waste material into a value-added product and yet lower down the carbon emission, that will be not only a very lucrative business, but also a very safer and greener environment as well.
And we can control the stirring speed, and we can control the temperature of the solution, and everything we can do it by using this instrument. And basically, once we add the fly ash in this reactor and we start stirring it, because this fly ash will be in the particular solution, we have to stir it to mix everything together. And we have the stirring machine here. This is the overhead stirrer to mix all together. And you can see like it's rotating. So by rotating this one, like you can mix the fly ash and the particular solution. The big filter for filtering the particular solution with the fly ash, and when you put here with the solution with the fly ash, the solution will come out, only the fly ash will stay on the top. Once we get the dry sample here from this oven, and with the dry sample we use it here for the mixture. Once we get the mixer, we have the mold to get the particular shape of the Zerocrete material.
Fly ash has a couple of main constituents. One of them is aluminosilicates. And we know the aluminosilicates coatings are very corrosion resistance coatings. So taking from the literature, having these constituents in the fly ash as a chemical makeup, we we foresee that this will be resistant to corrosion as well.
So concrete can be made greener. Now let's talk about making it smarter.
So in our lab, we work with smart materials, and our main goal is to develop new technologies, new devices to implement those in our day-to-day applications for different industries. SMA is one type of special material, and SMA stands for shape memory alloy. So you can use shape memory alloy for recovery of the concrete when it cracks, or it can be also used as a dampener, because when the shape memory alloy goes this deformation and recovery, it dissipates energy also. So it can be used as a dampener also in the concrete.
I have here basically shape memory alloys.
And then how could those be used in buildings?
So anytime you want a material that will go from one state to another, one shape to another, you can use shape memory alloy. Example in building materials, if you had a concrete column or any other structure that basically undergoes damage, so maybe it's bent, basically you can use shape memory alloys to recover its shape.
So we know shape memory alloys have some cool applications, but where'd they come from?
So their common term is called nitinol. And the reason why they're called nitinol is most of them are made out of nickel titanium, so NiTi.
Okay.
The nol part comes from the fact that they were developed at the Naval Ordnance Lab. And when they were developed, the reason why they found out that they were shape memory is a lot of the scientists were smokers at that time. So when they were smoking, one of them actually accidentally dropped a cigarette on the shape memory alloy, and the heat from the cigarette caused it to change shape.
So when concrete cracks, what happens is shape memory alloy gets elongated, and it can recover its shape in two ways. One is by applying external stimuli as heat, or either if the shape memory alloy is a super elastic shape memory alloy. In that case, it will recover its shape without application of external heat. So what happens actually is shape memory alloy, when concrete cracks, it goes into tension mode, and when the load is removed, it tries to regain. PZT is one example of piezo ceramic materials, and PZT stands for lead zirconate titanate. PZT is really interesting material. When you apply mechanical stress across it, it generates an electrical discharge. And it's vice versa also. If you apply electrical potential across the PZT, it undergoes mechanical deformation. So it can be used both as a sensor, like you compress it, it generates electrical discharge, or you can apply electrical discharge and it can work as an actuator, expansion and contraction. And in concrete, you can put those two PZTs around across some distance. You can send some wave from one PZT, it will travel through the concrete to another one will sense and give some electrical discharge. Now, if there is a crack in between, the strength of this wave will attenuate a lot, and this sensor will pick really small signature. So PZT in this case is being used for health monitoring of the concrete. This can be used as an impact detector also. If I keep away my sensor, and if I impact on this one, you can see it generates a wave. So you can embed this one inside a concrete, like a bridge column or a civil column, and if something hits that bridge column, that impact will be transferred to this sensor, and this can be connected to your safety system like electronics, and it will give you like, hey, there has been an impact. And then you can have these sensors and actuators talking to each other and trying to figure out where impact was, what was the severity of that impact. FBG is a fiber optic sensor, and FBG stands for fiber Bragg grating. It can be used for measurement of strain, it can be used for measurement of temperature, or it can be used for measurement of small scale displacements.
So this is the fiber optic sensor, FPG. So we have two portions here. You have the blue part, which carries the light. So what you will have in the actual application is you have a laser that would send the light within the fiber optic here, and the light will travel inside the fiber. You can see it's just like a piece of glass. And then it would travel all the way to the sensing portion right here, this small portion right here, and that will give you all the signals you need to measure your structure on the concrete. And so you can imagine something as thin as your hair being able to simultaneously measure the strain, temperature, and pressure. So this is the fiber optic corrosion experiment. So some of the background is that you might see a lot of concrete structures in your everyday life on the freeway, or the building you live in. Most of the time it's actually safe, but sometimes a very small crack might develop in the concrete and lets some water go in. The water might carry some corrosive agents that might attack the steel reinforcement inside the concrete. What happens is that the rebar, the steel inside the concrete starts to corrode and gets weakened. And when it gets weakened, it makes the structure more vulnerable to damage. And in extreme cases, it can lead to loss of life. So what we're doing here is using fiber optics to let people to be able to monitor corrosion. The basis of our sensing scheme is what happens to the thermal properties of a material when it changes. So in our case, the steel gets corroded and rust. So the actual material changes on the chemical level. And what this does is it changes its thermal properties. When the steel is healthy and not corroded, it will have a certain thermal coefficient and it will heat up a certain way. And when it's corroded, it would have a different chemical makeup and it will heat up differently. And we can compare these differences and find out how much the steel is corroded. And if it reaches a certain point, we can then alert the authorities and tell, okay, something's wrong, something's going on right here, we should check it out.
So if concrete, which is already the world's most used building material, can be made green, then I envision it being a much more valuable material and a material that doesn't necessarily have to be used for construction. We could exploit these other scientific possibilities given the properties that it has. It sets in water, it also sets at room temperature, it's durable. If we can make it they even have a concrete now that doesn't need rebar for reinforcement. If you can do those kinds of things, then I think the sky's the limit.
So what does the future hold for shape memory alloys? What's their next cool application?
Think about building a structure on the moon. You have to have excavators and dump trucks and all these things. So a lot of these different types of vehicles have hydraulic components, things that move on the vehicle. And so if we can replace those big, bulky hydraulic components with one shape memory material, basically we save weight and we save space.
What's the real challenge in realizing these materials?
These materials are really sensitive to their chemistry and then the way they're made. So with their chemistry and the way that they're processed, they can change their temperatures pretty dramatically. So,
and when you say temperature, you mean the transition temperature?
Right, exactly. However, they're very easy to control in terms of their mechanics and their understanding in terms of their metallurgy.
And once they're made, is that transition temperature stable for the fixed chemistry?
Yes, and that's what's also nice for outer space applications. They're very resistant to radiation, they're very resistant to extreme temperatures because they're basically a metal. And so they're resistant to a lot of different environments, even corrosive environments.
I think there are many more ways you can implement these smart materials in different ways to improve civil life. The best example is smart aggregate, which we started making using concrete, cement. We were putting the aggregate, but the orientation was changing. And later we found out what if we encapsulate inside two marble slabs. And we found out it works way better than what we have done before. So you see, as time goes, we are finding new ways to implement these smart materials in more smarter way inside civil structures. And I see that future generations will keep doing that.
So, if it were up to you, what novel ways would you use these new smarter and greener building materials? And how do you see them changing society?